There, ready. First things first, I changed the due date for the 4.6 assignment. So I do want to highlight, because otherwise I'll get freaked out messages. Hey guys, saying, you said you were going to change the due date, but you didn't. So, and I know why. So if you click on the assignment, it says it's now due on Monday, the 25th, which is the night before our test. So you need to have done it before the test, obviously, because it might be useful. I know, right? But if I go to my dashboard, it says it is due tonight still, but that's because they're not connected. I just put these up. So, but now if I go in to try to change it, it's going to say, well, you can't do that. It's going to erase all the completions of everyone. And so that's why I can't change it. Oh, it's for a different class. Yeah, I've got, that's the one you reacted to, huh? You didn't want the matrix algebra?
Wait,
you don't want you don't want to do, yeah, ANOVA. Yeah. Oh, a bonus assignment. I should post a bonus assignment for you guys. But anyways, usually what I do is I just set it to drop the lowest grade. If I post a bonus assignment, yeah, I should make a bonus assignment for you guys. Yeah. Assignment 4.6 is now due Monday, November 25th. I changed it. All right. We've got our test number 2 on November 26th. That's important. It's on chapters 3 and 4 only, although we kind of rely on some core material from 1 and 2, but kind of 3 and 4 explicitly. So I have not posted a practice yet. I'll post a practice for the test today, so you'll have it, because then we're a week out. And so same deal, I'll just grab from the assignment questions. That's why it has to be due before the test, so you can practice them. But they do look different when they're on paper, right? They kind of look, I don't know, harder for some reason, but they're the same. So I want a do-over of last day. And so we're going to do the dead body question, but we're going to use the time the body was found as the initial time point, and that's going to make it a lot easier. But also might be nice to do a little refresher anyways. So we were working with Newton's law of cooling, which is an exponential function, and it looks like this. So the temperature of an object T in surrounding temperature Ts is going to behave like this, where T is time, some unit of time. A is a constant, which is determined by the initial temperature of the object, but it is not the initial temperature of the object, right? We need to do a little bit of work to find the initial, or we're given the initial temperature, but then we need to find A, right? A little bit different from before. And K is a constant, which is the continuous rate of cooling of the object. So we were working on this, and I tried to get too fancy, and I flew too close to the sun. So when I gave up, now. Then I tried it again. It's fine. I just, yeah. I even got back to the office and I was like, I don't know. I completely flopped it. And I don't know why. It's just that kind of a day. Anyways, here we go. Let's do this. So a dead body is found. I think it's cuter when a turkey comes out of the oven or something like that, but they behave the same way, right? The turkey out of the oven is cooling, and a dead body is also cooling, right? And so I think there's a cheesecake one. They're all the same, right? And so its temperature was 85 degrees when found. So this is what we're going to use as our T equals 0, which is where I tried to be all cool about it, haha, pun intended, but it didn't work, or not with our skills at least. After 30 minutes, its temperature, sorry, the 30 minutes, do you know you have 30 minutes? After 30 minutes, its temperature was measured again to be 82 degrees. So here, T of 0 is 85, whoops, 85. And T of 30. Now, when I say T of 30, that's going to be, my time is now going to be in minutes. That's okay, as long as you keep track of your units. T of 30 is 82. If the surrounding air temperature is 60 degrees Celsius, no. That means TS is 60. When did the person die? Assuming the body temperature at time of death was 98.6 degrees. Good, because I'm running out of colors here. We want to find T when T of T is equal to 98.6 in the end. I think I made a note last day where we said, okay, well, if I use the initial, when the body was found as my initial point, then this T should be negative, right? Oh, thank you. T will be negative, which means it'll be the time before the body was found. Okay. Let's set up our empty formula and see what we can kind of plug away at. So I've got T of T is AE to the KT plus T subscript S. Yeah. We know T subscript S is 60. AEKT plus 60. And we're given T of 0 was 85, which if I do it kind of in a weird daisy chain kind of way, if I have T of 0 is 85, well, that's going to be the same as AE to the K times 0 plus 60. E to the 0 is 1, which means that 85 is A plus 60. So A is 25. Okay, so now T of t, plugging in that 25 e to the kt plus 60. We still need to find this k, right? That's the continuous rate of cooling. And how we're going to do that is the same way that we did for A, except now I'm going to use the second time point. We're also given, so now kind of phase 2, we're given T of 30 is 82. A is still 25. E to the k times 30 plus 60. I want to isolate the exponential function. I'm going to rewrite it as e to the 30k just because it looks a little bit nicer. But besides that, I'll move this 60 over to the 82, and I get 22 on this side is 25 e to the 30k. Oops. I need to divide both sides by 25 so that I can get that exponential function on its own. 22 over 25. Does that equal something nice? I suspect no. Wouldn't it be great if it did? 22 over 25. Yeah, it does. That's great. It's 0.88. E to the 30k. 0.88 is e to the 30k. Been a while, right? But how do we solve for k when it's in the exponent? We have to use a log of some sort, a convenient log maybe, log base e. And so I'm going to do it to both sides, the natural log of 0.88. And because it's our warm-up review do-over question, I'll write the log around the e. But because the reason you're taking the log of both sides is to bring the exponent down, you are allowed to jump to the next line. So you are allowed to jump down. But the reason I do write it out here is just to highlight that these guys basically cancel and the 30k drops down, but also you have to remember to take the log of the left-hand side. Right. Okay. K is so close I can taste it. K is the natural log of 0.88 divided by 30. Log of that guy divided by 30. I get a small k of negative point, scientific notation, 1, 2, 4. 1, 2, 3, good. 2, 6, 1, 1, 1, 2, 3, 8, 4. It's a compulsion.
So you want us to write every number as the answer, or shorten it a little bit?
So let's have a look. Let's have a look at this. How much of this do we actually need? I stop kind of gaining information after the 6, right? So that takes some practice, right? Because it's hard for me to say, oh, 4 decimal places. In that case, we wouldn't get very far. I'd be missing kind of the 6. But after the 6, right, 1, 1, 1, it doesn't really add anything. There's nothing of interest after the 6. And so for me, if you stopped kind of here, that would be fine by me, right? I guess I don't have a rule of thumb, but I guess internally, as soon as I don't have to round anymore, then I would stop, if that kind of makes sense, right? And so kind of technically could go shorter, but you do want to have kind of a good amount of decimal places because it's so small, right? So let's see here. Let k be negative 0.00426, which is what, 5 decimal places. So if you know how to use your store function on your calculator, then that's cool, you can use that. Or if you want to use a rounded value, just kind of make sure that you capture all the activity, and then you can use a rounded value. Either way is fine. I'll kind of, I don't really look at your final answer so much as I just care about your work, right? So as long as you're clear about what you're doing, right? Let k be this, okay, fine. You could say let k be negative 0.1, right? As long as it's a sensible value of k, right? It doesn't really matter to me. What's a sensible value of k? It has to be negative because it's decay, right? And k is usually very small because it's a rate as a decimal, right? So kind of reasonable values of k. But if you're ever stumped and you need to solve a question like this, maybe you get to this point, you find a, but then you're kind of trapped because you need k to solve the rest of the problem. Then you tell me, okay, I'm going to let k be, I don't know, 1%, right? Negative 0.01. Right? You don't get marks for this, quite a few marks, but at least you can answer the rest of the problem. Okay. So then t of t is 25 e to the negative 0.00426 t plus 60. So now we have the equation for the temperature, and now we can use it. We want to find t when t of t is 98.6. So let's force t of t. T of t is 98.6, but t of t also equals 25 e to the negative 0.00426 t plus 60. I'm going to store the entire value for k. I'll make a note. I stored it in a, and then I'll do a quick comparison of the differences. I don't suspect that there will be a lot of differences in the rounded and the exact value. But okay. So now I'm focusing on this equation here, and I want to solve for t. And so again, an exponential function, I need to isolate the exponential function. So I need to subtract 60 from both sides, then divide by 25, and then do what? And then take the log, the natural log probably. You could use log base 10, but it'll just make a mess. Then you'll have log base 10 of e, which isn't going to cancel away. It's still just a number, so it would work, but kind of messy. So I use convenient values of log base e. Okay. 98.6 minus 60 is 38.6 is 25 e to the negative 0.00426 t. I think I'm gonna need another page here. I suspect. Divide by 25. Oh, it's still nice. Wow. 38.6 divided by 25 is e to the negative 0.00426 times t. And this becomes 1.544, no rounding necessary, is this e to the negative 0.00426 t. Notice that we haven't used the value for k in our calculation yet, and so that's why I'm going to be able to compare the rounded value versus the exact value. So continuing here, because I have a new page, I'm just going to copy this. Copy. Hey. Copy, paste. Take the natural log of both sides. 1.544 is, should I just drop it down? Well, I have a whole new page. Why not just write it all out? This becomes technically, by the log laws, right? And the reason we use logs is because this, I can bring it down in front, right? So technically, in case you need that kind of a refresher, we get this. And this, of course, stays the same. But e to the power of what equals e, right? Remembering what the is going to be 1, right? So this here is 1, and that's why it goes away, right? Because we have e to the power of, let's see here, e to the power of 1 is equal to e to the power of 1. So that's why it cancels out. Okay, so now what I'm left with is t. If I use my revolving door, I want to have t, whatever I'm solving for, on the left-hand side, but that means that I'm going to divide both sides by this negative 0.00426, but then I'm going to switcheroo to the other side. And so I have the natural log of 1.4544 divided by negative 0.00426. Here's where I'll split. K is negative 0.00426 versus K is whatever is stored in A. So not rounded. Rounded to 5 decimal places. We'll compare the two. Why not? So here, in kind of this column, I get t is the natural log of 1.544. Remember, we didn't do any rounding there. Negative 0.00426. Start there. Natural log of that guy divided by negative 0.00426. I get t is roughly negative 101.9663032. So roughly 102 minutes. Now I'm curious because I don't suspect that using the unrounded value is going to make a huge difference, but let's try it. t is the natural log of 1.544 divided by store A. Shift. Oh, yeah. Recall A. Slightly different. Negative 101.939684. Can we push the envelope? What if I had just used negative 0.004? Now I'm just curious. All right. Let's see. What if I try k is negative 0.004? Lose interest after 4, even though it's followed by a 2, 6, kind of rocking the boat there. T would be the log of 1.544 divided by negative 0.004. Let's see here. I'm so curious. Oh. Okay, I better do it again. Divided by negative 0.004. Yeah, you're fired. I guess it's not the end of the world, but it is a large difference, right? And so here we're kind of just, we're still, gonna say 102-ish minutes, right? But here, 109 minutes-ish, or 108.5 minutes. I don't know. You'd be checking the wrong security footage. Right, and so this is quite different. And so you can play around with the rounding, but rounding the value can make a difference, right? And so I want you to keep as many as you can, or kind of as many as are interesting. Right? Okay. I don't think anyone would actually get fired over the difference between these two. There are instances where if we're talking about money and the units are in millions and you're off by $100,000, people get upset about that. So rounding is bad. Yeah. If your units are in the millions, I mean, come on. And so therefore, I don't want to talk about the murder. What's it say? I guess the person died. Bless you. Approximately 102 minutes before being found. Right? I've watched a lot of CSI.
Yeah, like I get caught like surely more than 2 hours.
Time to beat. Yeah, time to beat, I guess. 102 minutes. Now, to me, it feels a little bit wonky because we did all this work, not rounding any values, and then at the very, very end, we say, 102 minutes, right? But the reason we're able to kind of get wishy-washy at the very end is because we were so precise all the way throughout, and then we can kind of communicate it in something that makes sense. Nice. Any questions about that one? I will have a Newton's law of cooling question on the test. I can promise you that.
The whole test.
No.
Yeah, can the test just be the one question? This exact one though. Yeah.
I don't want to have a dead body. I'd rather talk about a turkey or a cheesecake or something.
The numbers.
You're gonna remember the numbers?
I mean, I just studied.
No.
Maybe.
Usually I do just change the numbers. I can have this one. But I don't like it. It's too gruesome. Dead body. Maybe a dead squirrel is found.
Yeah, it doesn't even say it's a human.
It's like,
This person.
Oh.
Yeah.
It's a dead body. I mean, it could be a fish.
It's definitely a person. Person.
maybe it's a bad guy.
Actually, that would work better.
Yeah, actually, I think I heard this story. This guy found like an orphanage.
I was actually.
Oh, well, yeah. Then let's use the rounded value for K. All right. Have you guys worked with log paper graphs yet?
Yes.
Okay, I have one yes, and I had a lot of head shakes no. So
Yeah, but we're not using. No, that's all. That's just the graph. That's a graph.
is it just the paper, or is it a function?
It's
We made a
log
log
paper.
graph. Draw lines on it, not like. We made a log
We
graph.
had dots, we put the dots on the paper and then drew a line.
Told the dots are.
We don't know what the function is.
Yeah.
Do you know what the lines are?
Straight.
I'm about to show you.
Yeah.
The reason we use logarithmic scales is to straighten out kind of bunch together values. So for any values that vary greatly in magnitude, okay, which is probably what you have in your measurements if you're using log scales, okay, things like the distance in millions of kilometers, I guess from what? From the sun. Yeah, I don't know. It's the distance. Who cares? I guess. I don't know. Yeah, maybe the sun. Does that make sense? It's just the distance.
No, because Mercury, so that would mean that Mercury is closer to the sun than Earth is. It is. Is it? Yeah. Oh, wait, yeah, you're right. I was thinking about backwards.
Let's clarify then. Distance from the sun. Yeah. Earth has issues. Yeah, exactly. So here we've got these distances, but obviously 58 compared to things like 2900, for example, those are hard to compare. So if we put them on just a linear scale like we would usually do, right, they would be all scrunched up over here, right? Most of these are kind of reasonable distance, are kind of similar distances from the sun, I should say. Not necessarily reasonable, but then we've got these larger order of magnitudes kind of later on, okay? And so the problem is that we get these kind of scrunched values, okay? So here the problem is the cluster of smaller values, which are there because we have to accommodate these huge values. All right, so here it's hard to tell what's going on here because the scale accommodates is there two M's, two C's, one of, I don't know. There. I think yeah, accommodates, I don't know, accommodates. Hey, score. Accommodates, wow, okay. The large values. Yeah. And so that happens a lot in things like chemistry and biology and anything where we have this kind of large range of possible values. So to get around that, what we do is we take the log of the distance. What does the log do? The log of the distance. So here, now log is log base 10 of the distance. So now, I'm gonna latch on to Venus Y because it's 108, which is nice, right? Because then log base 10, let's look at this one here. Still counts. Log base 10 of 108, really what we're looking for is, again, roughly 10 to the power of what makes 108? Just kind of rough ideas, right? 10 to the power of 2, we know makes 100. And so roughly, just if we had to use our trust our gut here, right? Roughly 2. In fact, it's 203. But what happens when we take the log of all these values, okay, they all kind of straighten out, right? And they're all kind of more evenly spaced. Okay? And so that's why you use your log graph, because it's already done the log for you. Okay? So let's see here. What's that graph paper called? Is it log paper? Log?
I think it's just
Log.
I think she did.
Well,
we had two, we had just, yeah, that one.
Oh, that.
Yeah. So there's kind of two options. You could have, usually you have your X and your Y's. Usually you could have a semi-log graph, which would have the log of Y, but still X, or you could have a log-log graph, which, you guessed it, has the log of Y and the log of X. Okay, so here we use the logs. Can I just circle this, I guess? I wanted to write something here. Need more space. We use logs so that the scale, I'm gonna say becomes in quotes, because it doesn't become linear, but it just kind of looks more linear. Maybe I'll say that to make the scale appear more linear. think it's technically in the next section, but what I want to do is we'll just do it. Oh. This little guy can go down here. If we have a function, right, that is exponential like this, let's say, right, it could be decay, right? But in this case, the distances are all kind of increasing. We've got quite a few down here, but then as we move out, right, the distances become further and further and further exponentially. This looks like this, right? F of x is a b to the power of x in general. We can rewrite this as y is a b to the x, making it a little bit nicer. Whenever I see f of x, I just read it as y in my head. And so now, when I take the log of y, what happens to this side? So now, if I take the log of y, then I take the log of a b to the x. I'm stuck with the log of y. That's fine. But what do the log laws tell us about multiplying inside the log? I can rewrite this as log a plus log b to the x. Right, that's a log law. Log of a plus log of b to the x. They'd be in chapter 4. I think 4.3. Chapter 3 wasn't it quadratics? Polynomials and quadratics. Mostly quadratics. Yeah. Oh yeah, it's been a while.
Yeah.
This is by the log laws. And I'll say 4.3 or 4.4 in case you need a refresher. But we also know by the log laws, if I have an exponent inside the log, I can rewrite that as a coefficient out front. Okay. Log of a plus x times the log of b. Does this look sort of familiar? If you kind of squint, this is just a number, and this is just a number. How about we call this number m, and we call this number b? This has the form of y equals mx plus b, right? And so taking the log of the output yields a linear function. So if you have kind of an exponential relationship like this, you could fit an exponential function to it, but most of the time, what's more convenient is modeling it with a straight line. So when we take the log of the y's like this, right, then I get kind of a straight line, so it straightens it out. So here, maybe I shouldn't use maybe I should be more careful. All right, b and m. Now the log of y has the form mx plus b, right, which is a linear function. And we spent a lot of time working with linear functions, is now a linear function. Whee! The trouble is the interpretation is a little bit tricky, right? Because your output is no longer in terms of y, it's in terms of log y, right? But that's why I use the graph paper, I think, so you don't have to worry about those interpretations anymore. Right? I think. Okay. Any questions about that one? Maybe I'll, fine. I can talk more about it. I really can, promise. I do want to say that instead of modeling an exponential relationship, sometimes, I would argue even often, but I'll say sometimes, modeling a linear relationship is going to be easier. I would say it's kind of residual from when we didn't have software doing all the work for us. Right now in Excel, you can just tell it to make an exponential function and fit an exponential function to your data. So it's not hard anymore, but it used to be very difficult. And so that's why, but also it's just kind of residual from that. But instead of modeling an exponential relationship, sometimes modeling the log of y as a linear relationship is easier. That could be easier kind of mathematically, or in terms of kind of explaining the relationship is easier to talk about a straight line, because most people have a decent understanding about straight lines, right? But maybe not so much about exponential functions. Okay. My little bit of stats sneaking in there. So if we have a scale, right, what value does the point plotted on each log scale correspond to? And so here I've got the log of x. So here we're told that the log of x is 3.25 in this case. So x must be what? We know how to solve for x, right? 10 to the power of 3.25 equals x. Or if you prefer to just have this, how do you solve for x when it's inside the log base 10? You raise both sides to the power of 10, you're going to get to the same place, right? Whether you want to read this as kind of an exponential function or actually kind of solving it. Either way, we get to 10 log base 10 of x is 10 to the 3.25, which means x is 10 to the 3.25, which is something large. What about this next one? I've got log of x, log base 10 of x is 10 to the negative 1.5. 10 to the power of 1 point, so 10, let's see here. This becomes, I have to do it like this. Log base 10 of x is 10 to the I don't like that. That doesn't look right. It is, let's do it, 10 to the negative 1.5, and then 10 to the power of that. No, I don't like that. I feel like we're missing, I don't think this is log, yeah. We'll stick with it. Do you mean 1.0755? Very good. But where do I lose interest? 5. I feel like there's some information missing here, but whatever. Whatever. Should I cheat? Blah, 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 blah. Hey. We were missing some information. This is from, so we're missing something here. But that's okay. We did it right, given the information that we had. I shouldn't assume my solutions. That's fine. Okay. Orders of magnitude. Has Allison talked about orders of magnitude? You guys? So what she said, so I was like, what do you need? What do you need from me? She's like, well, they need to know orders of magnitude, which is kind of this logarithmic scale. It's kind of all encompassing about the logs, the semi-logs, all that kind of fun stuff. But also how these things are related by orders of magnitude. Okay? And so orders of magnitude look like this. So if we have two values, A and B, then to determine how many orders of magnitude A is greater than B, what we do is we take the log of A over B. So the log of A over B, you can rewrite as what? The log of A minus the log of B, but this is shorter, so we use the A over B, right, by the log laws. So the difference in the orders of magnitude is going to look like this. Okay. So for example, now I'm drawing a blank on my example. I'm gonna steal it. Okay. You know what? We can do better. Let's compare the orders of magnitude of, let's say, Saturn to Neptune. in terms of distance from the sun. Gonna copy this, copy. Paste. Which one did I say? So let's do Saturn and Neptune. Why not? We can let, so if we have two values, A and B, so in this case, we have A is going to be 4,500. Why? Because we want to know how much A is greater than B. Okay. So I'm going to let this be A and this be B. Because of the greater than here, so A is greater than B. Then the difference in orders of magnitude, oops, is the log of A over B, which is going to be the log of 4,500 divided by 1430, which we're just going to use our calculator, of course. And it is log base 10, right? When it's just written log, that's the common log. So it's log base 10, 4,500 divided by 1430. Take the log base 10 of that. And I get 0.497876476, roughly. So the difference in orders of magnitude is roughly a half. What does that mean? Really what it means is, oops, 10 to the power of 0.5, right? 10 to the power of 0.5 is 3.16. So if I go from 1430 times 3.16, I get 4522. Yeah. So it's the difference in the orders of magnitude. And we can rewrite do I want to go down this rabbit hole? No. I don't. Or do I? Yeah, let's see here. Okay. So now if the difference in order of magnitude is roughly 0.497876. A lot of activity there. Let's go there. Then what can we do? That's the log of A over B, right? And so we can take it back and we can say, okay, 10 to the power of 0.497876, 10 to the power of 0.497876, I get roughly 3.146849696, which we can confirm, right? B times A copy. B times this guy. So times 1430 is 4499.995065, which is basically A. So that's the relationship. Is this the real time or?
Completely wrong.
Way off.
What's probably the closest hour?
But that's bad in this case, then it'd be 9. The closest hour.
That's true.
Oof.
Well, 9:06 is basically.
Until 9:31, then we're done class.
It still kind of works out.
It
That's what
does.
your goal is.
On average, right?
Like right now, it feels bad, but kind of like give a little, get a little.
Yeah, you'll get through it. You'll get through it. So orders of magnitude are kind of common with earthquakes and things like that. And so let's see here. For an earthquake with seismic moment S, a measurement of earth movement, the MMS value or magnitude of the earthquake is M, which is 2/3 times the log of S over S naught. When you've probably seen, I feel like we've seen a subscript 0, which is a naught, kind of an initial point. So this is S naught or null or 0, which is kind of always a starting point. I'll say initial value. So S naught is always going to be 10 to the power of 16, which is a baseline measure for seismic moment. Okay. If we have one earthquake that has an MMS magnitude of 5 and a second one has a magnitude of 8, how much more energy was there in the second earthquake? So how much more energy? Let's see here. We're given M for both of these, so let's just start with that. Let's start with earthquake number 1 and earthquake number 2. Gonna pick apart the information that we have, and then we'll kind of take a step back and see what we might need. So we're told that M is 2/3 times the log of S over S naught. S naught is always 10 to the power of 16, right? And so, and what I'm gonna do is earthquake number 1, I'm gonna denote it by S subscript 1. From here. Because I'm also going to have M is 2/3 times the log of S over S naught, but this is for earthquake number 2, so I'm going to put a little subscript 2 there. We know S naught is 10 to the 16 for both of these. And earthquake number 1, let's see here, had a magnitude of 5. So we have 5 is 2/3 times the log of S1 over 10 to the 16. And the second earthquake had a magnitude of 8, which is 2/3 times the log of S2 over S naught, which is 10 to the 16. I wonder if we should just keep it as S naught. We'll see. Doesn't matter. How do we solve? We know how to get at S1 and S2 individually. Okay. And so let's see here. First thing I need to do is I need to isolate the log in both instances. So I need to multiply by 3 and divide by 2. And so I get 5 times 3 divided by 2 is 7.5 is the log of S1 over, I'm tempted to write just S naught, but let's do 10 to the 16. Stick with it. 8 times 3 divided by 2, if we do these in tandem, 8 times 3 is 24, divided by 2 is 12, is the log of S2 over 10 to the 16. Now I've isolated the logs, and so now how can I get at the s's inside? I can take 10 to the power of both sides. So 10 to the 7.5 is 10 to the log, but the reason I'm doing the 10, so I'm going to skip it, is to get at the inside, right? 10 to the log base 10 of this thing just drops down to be s over 10 over 16, or 10 to the 16. S1 over 10 to the 16. And then same thing here, 10 to the 12 is S2 over 10 to the 16. Bless you. Okay. I can rearrange these in terms of S1 and S2. So this is where, if you wanted to, you could have just used S naught here and S naught here. Because what's this going to look like? This is going to look like S1 is 10 to the 7.5 times 10 to the 16. Which you could add those powers because you have the same base, or what you could say is you could say, or 10 to the 7.5 times S naught, which is a little bit cleaner, maybe. S2 doing the same thing, 10 to the 12 times 10 to the 16, or if you prefer, 10 to the 12 times S naught.
Wait, why is that S naught?
It's just a fact. Yeah, here. Okay. So now I have S1, I have S2 in terms of just massive numbers, but I want to know how much more energy was there in the second earthquake. So in terms of orders of magnitude, right, I'm going to have the log of the bigger one over the smaller one. So I want to find the difference in order of magnitude is the log of S2 over S1. We just solved for these. And either way, and I'm going to bump it over here, because this is going to be the log of 10 to the 12 times 10 to the 16. And I'm not simplifying them on purpose because they're about to cancel, right? Divided by 10 to the 7.5 times 10 to the 16. Or the log of 10 to the 12 S naught plus 10 to the 7.5 times S naught, if you wanted to keep them there. Either way, they're about to cancel here. Dividing by the same number, and there's only multiplication going on. Or technically, you could float this 10 to the 16 upstairs by rewriting it as 10 to the negative 16, and then you'd have 10 to the 16 minus 16 is 10 to the 0, which is 1. Either way, that's how it cancels. Doing the same thing to the denominator now. Either way, if you just use a bare bones S naught or 10 to the 16, they're going to cancel, and we're going to be at 10 to the power of 12 over 10 to the 7.5. No matter how you got there. This, I can simplify this. Whoa. This is the same as the log of 10 to the 12 times 10 to the negative 7.5, because it's been a while since we worked with exponents. And so I have the same base, which means I can add the exponents. The log of 10 to the 12 minus 7.5. 12 minus 7.5 is 4.5. The log of 10 to the 4.5. 10 to the power of what equals 10 to the 4.5? I'm going to go with 4.5. You can use your calculator. But that's the difference in the order of magnitude. But the order of magnitude, we can translate and we can say, okay, 10 to the 4.5, 10 to the power of 4.5 is 31622.7766 is how much more energy, right? This is the difference in order of magnitude of energy. So then I can take that here, 10 to the 4.5 is the actual difference. Is the difference in energy. Nice. I guess I've ditched units. I never had them. That's okay. I am gonna leave this one for you to try. It's very similar, but you kind of work the previous problem backwards, okay? Because I want to do some flow duration analysis. I don't know why I didn't capitalize the D. Which is just using the log scales. Now let's see here. Have you done flow duration analysis yet? Maybe. I don't know. I just okay. That's okay. Allison did just, I guess this was a few years ago, but she said, you know, if you could talk them through the math part, I can talk them through what it's doing. And so that's our deal. So I'll talk you through the math part and kind of the procedure of what's going on. And then I'll leave the actual water stuff to Allison because I don't know water stuff. So flow duration analysis is we're going to plot a flow duration curve, okay, which is going to show a percentage of time that flow in a stream is likely to exceed or to equal or exceed some specified value of interest. And so we can use it to show the percentage of time river flow can be expected to exceed design flow or some specified value, whatever this is. And so my job is to talk about how is it calculated. Okay. Now the procedure is relatively simple. Okay. If we have some flow, and I gave you a, let's see here, download maybe. See if it'll open it on my iPad. Whee. Here's some data that we have. Okay. We have a location number. Thank you. Thanks. So we've got a location number and we have the minimum flow over some time period. Okay. Now, step number one is you're going to sort or rank. They're kind of the same, but you're going to sort the flow amounts from the largest value to the smallest value. And you'll have a total of n measurements. So in this case, if we go back here, hey, it ditched my workbook, but I wanted it. Uh-oh. What have I done? Where is it? You recently opened this. No. Here. Okay. Let's see if I can pull it off on my iPad. It's going to look a little bit different, but I want to sort these guys, of course, keeping the location number because that's how we know where it was going on. Sort from largest to smallest, right? So descending, and just double check that it brought the location number with it, which it did because it was previously sorted by location. Okay. And so now what you're going to do is you're going to assign it some rank. How do I type on here? I can't seem to type on here. Here. There we go. Show keyboard. Nice. This is going to be 1. This is going to be 2. And hopefully it'll just keep going. Nope. Not with my finger, it's not. Hey, why isn't it doing it? Okay, not great. I did bring my laptop for this reason, but I didn't want to change gears. And now I drew on here. Oh boy. There, pre-baked. Now, of course, I can't get rid of my keyboard. Yeah. Okay. So we added a serial number, which is called M. Yeah. So that was step number 2, I want to say. Yeah. Assign each discharge value a rank M, starting with 1 for the largest daily discharge value, which is what we did, right? So this was the highest, and then we went down to the lowest. Now, this, we did that. I'm gonna check off the steps. Then we're going to calculate the exceedance probability. Now, kind of the statistician in me has a hard time with the probability part, but I guess it is technically a probability. But all it is you're taking the rank divided by however many locations you have plus 1. You know? And so P is going to be the probability that the given flow will be equaled or exceeded, right? If we think about if we have the first rank 1, over the total number of points plus 1, right? That's going to be the smallest possible value, right? Because it's the largest, the probability of exceeding it is going to be the smallest, right? And so here, consider M equals 1. Then P is going to be 100 times 1 divided by, how many N's did we have in our case? We had 22. So 22 plus 1 is what we're going to use. That probability is 1 divided by 23 is times 100, I guess. Usually we don't do 100 for the probability. That would be the percentage, but that's okay. Probabilities are between 0 and 1. 4.3478%, right, is the probability that the flow is going to exceed it, let's say, equal or exceed that amount. Very small. In fact, it's the smallest. So then, and the minimum flow, the probability associated with these, right, is going to increase as the rank increases, right? Is then the flow gets lower and lower, and so the probability of exceeding it gets higher and higher and higher. You know? Now, what we have, we can fit a linear model to this. It doesn't fit very well, does it? Right? We can have the probabilities are on the x-axis and the minimum flow, which is the output, is on the y-axis. And so now I have a linear equation, which we've seen before, right? I've got an r squared of 0.7118, but I also notice that, okay, this line doesn't model this relationship very well, right? It's hard because I don't have a pointer in Excel, but I would want to capture this kind of relationship here, right? This looks like a decay style relationship. Right? So what do we do when we live in a shoe? We can fit an exponential model. You can do that. That's easy enough in Excel. In fact, I'm going to try it on my iPad unsuccessfully, I guess. I don't want to. Okay. I knew it. Should have busted out my laptop. I had the chance. But we're pretty close to rounding up to 10, so. Well, I wonder if I can copy this. Copy? Haha, score. Oops. Paste. Oh, yeah. So here, now we're cooking with gas. The linear model doesn't look that good. I know. What I want might be something like this. That wasn't very good either. Okay, let's see here. Kind of. An exponential model would be better. Or we can take the log of y. Usually what we do is we take the log of y first, and then if it still looks exponential, then you can take the log of x. So 1, take the log of y, and then if it still doesn't look linear, then you can take the log of x. I suspect what's going on in fields like water engineering is they know what the relationships look like. And so then they just know that they're always going to have to go to a log-log scale, for example, bless you. And so, right, if you know about the underlying relationship, then you just always know what to do. But if you're exploring it, it's not as easy. So now, if you take the log of both, so this is the log-log graph that I gave you. So then I've taken the log of the flow and the log of the probabilities, and it generates this kind of more straight relationship or linear relationship. So here we've got a log-log graph. But you can also play around with the exponential model fitting in Excel. The same way that you fit a linear model like this, which we did way back, quite a while ago now. Right, you right click on one of the dots and then you say add a trend line, and then it'll give you the option to pick a linear equation or an exponential equation. And so then you can kind of play around with those. Notice that our r squared has increased by quite a bit, and it looks relatively linear, not beautiful, but kind of linear. And so then the r squared actually tells us something. 92.04 is really high, right? You want to have an r squared as close to 1 as you can, but 92 is, or 0.92 is really high, so I'm happy with that. Okay. So the math is in fact not that bad, right? You sort your flows from largest to smallest, you add a ranking number, calculate the probability associated with each rank, right? Making sure that you remember to divide by n+1. And then you can use that on your x-axis usually, right? P usually goes on the x-axis. Because we're interested in the flow, right? Not the probability. Although you could switch it up, doesn't matter. Just how you read the graph. Okay. I think we're ready to round up to 950. How about that? If you have any questions, let me know. Otherwise, I'll see you on Thursday.
On Thursday, are we going over
Yeah, I'll do a run through of the practice test, but I suspect that you won't have time to practice it. Even if I post it today, you won't have time to practice anything. But if you do have questions about it, maybe just have a glance at it before Thursday, because then you can ask me questions like, I don't remember how to do this one. And so I'm happy to go through that. But otherwise, we're going to start circles in chapter 5.
Hey, Emily.
Oh, yep.
I was wondering about 4.6. If we could maybe get an extension for a day or two for the quiz.
Already done.
All right, perfect.
2-minute beginning, bro?
Here. Oh, I'll show you. Let's see here.
Is Josh on there?
Here.
Josh, if you're
It's
on
now
there,
due on Monday, November 25th.
Perfect. Thank you.
Yeah, you bet. Let's
Josh,
see
if you're-
here. I'll stop this recording so we're not